In this video, we are going to look at charged particles in magnetic field. Now, in previous video, we have seen that if there is a conductor which is carrying current is placed in a magnetic field, that it experiences force. Now, a conductor which is carrying current, it actually means there is charged particles moving within that conductor. So and that conductor is experiencing force. So we can assume that we can draw inference that charged particles, if they are moving in magnetic field, they will also experience some force. Now this force is given by, we'll go straight for the expression, and expression is F is equals to QVB sine theta. Now Q is equals to charge, and that is in coulombs. V is equals to velocity. It should always be in meter per second, and B is magnetic field, and that should be in Tesla, and theta is the angle between B and V. Now we can infer from this equation that if V equals to 0, then F equals to 0. So stationary charge would not experience any force. Okay, further we have seen that in case of conductor, that the force, I think I'll write it in case we saw that F was perpendicular to both B and I. The same is the case here. In this particular case, let's say force on charge, we know that will also be F is perpendicular to both, let me write in this same order, B and velocity. Right? If we just talk about F and V, let's see what we come to. So we see that F is always perpendicular to velocity. Now in case of conductor, the direction of B and I was fixed, because whatever was the direction of the current initially, that remained. But in case of charge here, as the charge is moving, there is a force always acting perpendicular to velocity, which means that the velocity would change. And we know that if whenever the kind of motion in which force is always perpendicular to velocity, we know that that kind of motion is always circular motion. So let's continue our discussion. We have a charged particle. Suppose this is my charged particle, maybe proton or electron or any other charge, and there's a magnetic field around here, all here, maybe out of the board or something like that. There's a magnetic field, and because of this, because the charge is moving here with some velocity, there's a magnetic field here. So this charged particle would experience a force which would always be perpendicular to velocity. So this particle would basically move in a circular direction. And why it is moving in circular direction? Because it has got some centripetal force acting on it. And where is that centripetal force coming from? This centripetal force is coming from this magnetic force. Let me write like this. Let me call magnetic force is acting like centripetal force. So let's suppose that our charged particle goes in a circular motion with radius r, small r, let's say radius r. Then the centripetal force is equals to Fc is equals to mv square over r, where m is the mass of the charged particle and v is its velocity and radius r is the radius of circular path. So if the particle is moving in this circular path, it would need centripetal force, and that centripetal force is basically is provided by the magnetic force. So in our case, we have because this is magnetic force here, there's a centripetal force, this is the magnetic force. In our case, we have seen that theta is equals to 90 degree. Therefore, sine theta is equals to 1, and therefore this equation now becomes mv square over r is equals to qvb. We can solve this. We can simplify this equation and find the radius of the circular path that would be followed by the charged particle in magnetic field. So we just want to get r all by itself. So let me write it here. We want r all by itself. So let me multiply r here, both the sides. Then from here I want to get rid of this qvb. So I'll divide by qvb here, and that equation will give me this cancels with this, r cancels with r. So I am on the left hand side, I am left with mv over qb. On the right hand side, I'm left with r. This is a really important expression, and it gives us the radius of a charged particle when it is moving in magnetic field. Now, how do we find the direction of this force? The direction of the force. We talked about the force here. How would we find the direction of force? Right? We just discussed that force is equals to, sorry, it is not E, the letter is F is equals to QVB sine theta. But how do you find the direction? The direction here is, we use the same right hand palm rule, but always keep in mind that we are talking about instantaneous velocity at a particular point. So again, we follow the same rule, our right hand palm rule, thumb, it gives you direction of V at that particular point of time, or that particular point, specific point we are talking about, because it will always be changing. And fingers gives you direction of B, and then we know that perpendicular to the palm is the force on the charged particle. Okay, let's look at a few examples here. So let's look at a few examples here. Suppose I have, this is my magnetic field, and it is here. Basically, it is in this space, and it is perpendicular to the base, entering into the base. And now a proton is launched in this in this magnetic field, and we see that both are the velocity of the proton and the magnetic field, they are at 90 degrees with each other. We can apply right hand palms rule here. If we put our thumb in a direction parallel to the velocity and fingers in a direction perpendicular to the pace, going into the pace, and we see that the force on this proton at this particular point will be in this direction. Yeah, that's my force. Again, because the velocity will change, so force will always change. So I'm just talking about at this particular point. At this particular point, this is the velocity, and the magnetic field inside is into the pace, so F will be like this. And that's how it is going to be like. So the proton will move in a circular path here and come back out here. All right. What about if suppose I have, this is my magnetic field this time here, coming out of the board, coming out of this page, and I'm launching an electron here this time. Now electron is negatively charged, so what would you do here? So the velocity, that's my velocity vector, and I need to find the force. So when the charged particle is negative, all we do is we still use the right hand palm rule, but when we find the direction of force, in case of charged particle, we just reverse the direction. So suppose this, instead of electron, this is a proton, and then it has got velocity in this direction. Magnetic field is out of phase. So using right hand palm rule, we'll see that the force will be in this direction. But that would be in case of proton. So now because we are considering electrons, so we just reverse the direction of force, and the force on electron will be in this direction. So, and that's how it will always be. I mean, even if it moves a little bit, velocity changes, but it will go in a circular path and come back here. So that's my electron. So both of them will follow a circular path and they move in this direction. Let's look at one more case here. So suppose we have magnetic field here going into the page, and we send three particles here. We are sending a mixture of particles. Basically, we got electrons here, we got protons here, and we got alpha particles. Alpha particle has got a charge of 2 units, and they have a mass of 6 times that of proton. All right, so we can see in what direction each of these would move, and we need to draw their path. Now here we'll also need to take into account the radius. So first thing, we can see that when my velocity is like this, the force on a positive particle, just using the right hand rule again, thumb extending in the direction of velocity, fingers extending in the direction of magnetic field, which is into the page, and I see that for a positively charged particle, the force will be in this direction, and the positively charged particles will move in this direction. And likewise, negatively charged particles will move in this direction. Right? Once we have determined that, now we need to determine the velocity. Now we need to determine the radius. So just to say, positive particles will go in this direction, negative will go like this. Okay, now we need the velocities, radius. So we see that here, all of them are, we are assuming that velocity of all these 3 particles is same. So electron's mass is very small here. So in case of electrons, because electron is almost 2000 times lighter than the proton, so mass is very small. Mass is very small, So electron's radius here would be very small. So I will just draw it. That's our electron going like this. Next we consider the proton, and we see that proton is 2000 times bigger than electron, and charge is same. So proton's radius will be much bigger than electron, but we don't have more room here, so we'll just draw it like this. That is my proton. And what about alpha particle? Alpha particle is has six times the charge of a proton. So mass is got very huge mass, so radius will be bigger. But then charge is also huge, charge is more, but it charges only 2 times bigger. So effectively, when you take both of them into account, mass is 6 times, charge is 2 times, then radius will be still bigger than the proton, and the radius of alpha particle will be like this.